Hello everybody, my name is Rhyd Lewis. I'm a reader in mathematics at Cardiff University. In this video I'm going to talk to you about how sat-navs work, and I'm also going to introduce some graph theory and show how graph theory is used to help the mapping software used in sat-navs. So networks are mathematical objects that we encounter in many walks of life. They're very simple to understand. They're basically diagrams, if you like, of entities that are connected in some way. So things like social networks, road maps, chemical bonds, and things like that. So here we have, as an example, a social network made by a middle school and a high school. You can see each circle here is a person, and we have lines between people if they have specified that they're friends with one another. And you can see here we have some clusters. So here we have the middle school students, and here we have the high school students. So there is certainly more links between students in the same school, but there's also links between them as well. So these tend to be called things like nodes and links, or edges and vertices and so on. And let's not get graphs confused with the other type of graphs, things like bar charts and pie charts and so on. We won't worry about that. We're just talking about these sorts of networks. Okay, so as a small example, here is the geographical layout of tube lines and stations in the Greater London area. You can see here that things are very bunched towards the centre of the graph because that's where there's more stations, but it's not very helpful for helping us to navigate our way around London. Instead, we tend to use a graph that looks like this. This is showing the connections between stations, but we're not so worried about the geographical layout. As you can see though, it's much easier to find our way between stations using a graph. So the important thing to note here is the connections between the nodes. Okay, so let's move on to sat-navs. So how do sat-navs work? Well, firstly, we need to figure out where exactly we are on the Earth's surface using GPS, global. So in fact, what we have is about 6,000, currently about 6,000 satellites orbiting the Earth. Many of these are geostationary satellites, which means that relative to a position on the Earth, they are standing still. So they are moving around the Earth at the same rate that the Earth is spinning. So in effect, they are above the same point in the Earth the whole time. So we have a satellite like this on the right-hand side. And each of these satellites, they continually broadcast a speed of light, speed signal, saying where they are. So they are broadcasting a signal and they are saying where they are. Now, if I have something that can pick up that radio signal, I can compare the time that it was sent to the time it was received, and I can then work out how far I am from that satellite. So here we have a satellite that's outputting some signal. Let's say I received it a few milliseconds later, which means that I can calculate that it's 10 kilometers away. I know now that I am somewhere on the circumference of this black circle because I am 10 kilometers away from this satellite. Okay, so I'm somewhere here. If I then use a second satellite and I can figure out that I'm 5 kilometers away from it, I now know that I must be either here at this intersection or here at this intersection. If I add a third satellite, then I now know where I am. I can figure out, using these three satellites, my exact point on Earth. This is actually called triangulation. This was used in ancient times by sailors trying to figure out where they were by looking at landmarks and judging their distances. It's a little more complicated with sat-navs on the Earth's surface because we also need to figure out our height as well. So we might need a fourth satellite, and this is known as trilateration, but the concepts remain the same. So we have these satellites broadcasting their information, and as many people who want to use them as possible can use them on the Earth's surface and figure out their coordinates. So there's no limit to the number of people who are using these signals. So now I have a GPS coordinate, so my sat-nav knows where I am. So imagine now I'm at point A here, and I want to figure out how to get to the shop at point B, and I need the quickest route. So what we have here is a graph that is representing the road network between A and B. So this is maybe a road that travels for 2 kilometers before we get to this junction, and then 5 kilometers here, 5 kilometers here, and so on. And I want to find the quickest way from getting from A to B. So how do we do this? Well, human beings are very good at doing this by just looking at maps and sort of judging which is the quickest route. But of course, computers don't have the abilities to make those sorts of heuristic judgments that we have. Instead, we need some sort of more methodical way of determining the shortest path and guaranteeing that that is the shortest path. So here we're going to use a little algorithm known as dijkstras algorithm, which is one of the best known shortest path algorithms. So how does it work? Dijkstra's algorithm starts at the starting point A, and it labels the vertex as 0, which basically means the shortest path from A to A is 0. All the others are marked as infinity. What we then do is we then look at all of these connections here, and we can see the quickest way from A to this vertex here is 2 units, 3 units to here, 3 units to here. So we change the labels to reflect that. And now we mark A as red, and we don't need to consider it anymore. The next step, what we do is we look at the vertices and we choose the one with the lowest label. The lowest label here is 2, and we mark it as red, and we update the labels of the vertices here, this one and this one. So this now gets updated to 2 plus 5, 7, 2 plus 5, 7. And there we have, we've updated the labels. Now we repeat the same thing. We find the shortest label again, this time here, and we carry on updating the labels. And as you can see, slowly all the vertices are turning red, and we've got to B now, and we have found our shortest path. So our shortest path from A to B is 3 plus 1 plus 2 plus 1, 7 units, 7 kilometers from A to B. So our sat-nav has combined 2 technologies there. It has combined GPS with mapping software and shortest path algorithms. So now we can just press a button on our sat-nav and we move. We know the quickest way to get from A to B. Now these algorithms are very efficient. So we've probably used Google Maps and Bing Maps before. So just before this presentation, I typed in the quickest way to get from Hay on Wye in South Wales to Seoul on the other side of the world, capital of South Korea. And as you can see, very, very quickly, in less than a second, Bing Maps has used something like Dijkstra's algorithm to find a very, very short, efficient path to get from A to B. Now, it's obviously not short if you wanted to drive it, but this would be the shortest possible route that you could take if you were to try to make this journey. Okay, so I hope that has provided some illumination into graph theory and the use of sat-navs. Thank you very much.